In this video, I'm going to be explaining sound and its characteristics, as well as how it is produced, how we hear it, how it travels, and the different components of sound itself. Question 1. How exactly is sound produced? Sound is produced when an object vibrates due to an external force that transmits energy in some form. When the force is applied, vibration, however evident or not, does occur. A vibration is a movement back and forth about an initial point of rest. We see this when my instrument's string vibrates up and down when the energy from my finger is applied to the string, and it eventually comes to a stop again. This concept is also demonstrated in this diagram I drew. As you can see, before the sound, the strings are shown as being completely still, because no energy has been applied. When the finger is being pushed down, it shows how the string is slightly bending from the energy from my finger. After it is plucked, it shows the path of the vibration, which eventually comes to an end, and after a while, the string is back in its starting position. Energy in science is the ability to do work, and when energy is transferred to the object, it causes it to vibrate, like my finger to the string. The vibrating object causes the surrounding medium, such as air, water, or solid, and its particles to vibrate, creating sound waves that eventually reach our ears for processing in the brain. This simulation is a slow-motion version of what you might actually see if you could see particles in a medium vibrating. A sound wave is created by the movement of energy traveling through the particles of a medium as the energy travels away from the sound source. These waves are what reach our ears and enable us to process and essentially hear the sound. Sound waves are products of the vibration created by the object. Question 2. What exactly are the scientific parts of a sound wave? The scientific parts of a wave consist of the starting position, amplitude, peaks, and valleys. The amplitude of a sound wave determines the loudness of the sound. It is scientifically the displacement of the wave from its starting position. The larger the amplitude, the louder the sound, and vice versa. Peaks are the highest point in a sound wave, and valleys are the lowest point. As shown in the diagram, the starting position, or the equilibrium of the wave, is its point of rest. This is where there is no movement or vibration. The pitch of a sound is determined by the frequency of the waves. Pitch in everyday language is how high or how low the sound is. Frequency is the number of waves produced in a set interval of time. The higher the frequency, or the greater amount of the waves produced in a time, the higher the pitch of the sound. The lower the frequency, or the lesser amount of waves in a time, the lower the pitch of the sound. These concepts are demonstrated in this computer model that I've shown in this video. As you can see, as the slider of the pitch is increased, the waves get closer and closer together, meaning that the number of waves per second has increased as well, and the frequency has increased along with the pitch. Vice versa, as the pitch is decreased, the waves slowly spread apart, showing that the frequency is decreasing and the distance between the waves is bigger. As you saw and heard in that video, as my fingers moved up the fretboard to the right, the pitch increased, and as they moved back down to the left, it decreased. Assuming the same tension, the pitch changes because the longer the string when plucked, the lower the pitch, and the shorter the string when plucked, the higher the pitch. When my hand presses down on the fretboard, the string essentially shortens in its length because my finger cuts off where it vibrates from. When the energy from my finger is applied, it then vibrates and produces a higher pitched sound. This is because the shorter the string, the higher the frequency, because it vibrates faster and more than when the lower string is plucked. This is one example of how pitch and frequency together is demonstrated in my stringed instrument. These graphs demonstrate how frequency and pitch are correlated. In this graph, the y-axis is the distance and the x-axis is time. As you can see, as the pitch is increased, and a greater amount of waves is produced in the same time frame than when the pitch is decreased, meaning that it has a higher or lower frequency. More mathematically speaking, you can see that in a lower pitch, in roughly 0.02 seconds, only one wave is produced. Then in a higher pitch, when in 0.02 seconds, roughly 4 waves are produced, showing that one has a higher frequency than the other. Overall, thanks for watching, and I really do hope that you learned something new about sound that you didn't know before.